let's flip the titration around now. Rather than titrating, having my titrant be a base, let's have our titrant be a strong acid. And so what we're going to do is we're going to add a strong acid to a weak base. And so we'll take our 25 milliliters of ammonia, and to that I'll add HCl. And we're going to continue with the same concentrations we had before. Okay. Now, for my initial pH, before I add any HCl to my ammonia, I have to do an equilibrium calculation to determine the degree to which it has caused a hydrolysis reaction. Okay, and from my calculation, I can get my concentration of my hydroxide, and I can get my pOH, and because we're plotting pH, we'll just invert it. So we're starting off with a higher initial pH. Okay, so you can see it plotted here. Now, when we're titrating my strong acid with my strong base, I'm not going to end up with a salt plus water. I'm going to end up with ammonium ion and a chloride ion at my equivalency point. So I've added enough HCl to consume all of my NH3, and it's become NH4+. Okay, now my volumetric equivalency can be determined stoichiometrically just like before. Okay, but my pH at equivalency, we have to fall back on the theory that we learned last week. We know that my ammonium ion can act as a conjugate acid and it can donate the proton that it has gained, whereas my chloride ion is too weak a conjugate base. So we know therefore that because my ammonium ion can act as a conjugate acid and it can produce hydronium ions, my pH at my equivalency should be less than 7. Okay, so now if we want to determine our pH at our half equivalency when we've added 12.5 mils of our acid, so in this case we're going to assume half our moles of our ammonia has become ammonium. Again, we're going to reject any hydroxide that was produced because it will have reacted with any of the protons from our acid that was added. So I can determine my total moles of my ammonia. Since half of them are consumed, I'm left with half, so I can divide that by 2. And then I can determine the concentration of my ammonia after. And because we're saying half my ammonia became ammonium, their concentrations will be equal. So now that I know their concentrations, I can set up my ICE table and substitute my values in. Because our Kb value is so small, we'll do our check. We'll probably find that x is not significant, so that'll allow us to simplify, and we'll find out that our x value is equal to our Kb, which we can then obviously do our proof, and then we'll find that. And so my pH is equal to my pOH, and again my pH. And so for weak bases being titrated by acid, what we find is that my pH at my equivalency is actually going to be equal to 14 minus pKb. Okay, so we can plot that value on our graph. Okay, now if for my final pH, I'm going to add a large amount of HCl. I'm going to approach the concentration of the HCl, but because of dilution, we'll never quite reach it. So I'll have a pH of approximately 1 that I'll approach, but I'll never quite reach. Now, I calculated values just so that we could see the shape of our curve. And so if we add our values prior to our titration, our equivalency point, we can see that we have a region where we rapidly come down initially, and then we come down at a much slower rate until we get close to our equivalency point, and we have a rapid decrease. We have our equivalency point with pH below 7. And then we have after. And so then we can replace it with a line. So we can see this is the shape of our curve for a weak base that's had a strong acid added to it.